Every ray of light that is radiated by him makes him shine in the wide world. Now I invite our chairperson, Professor T. Mohandas, Dean, School of Basic and Applied Science, Head, Department of Chemistry, Central University of Tamil Nadu, Tiruvarur, for the debut of Chief Guest Speaker.
Morning to each and every one of you. Uh, at the outset, I thank the organizing committee for this particular opportunity because I'm happy to introduce one of the eminent scientists of India. And I'm sure like most of the senior people may be knowing about Sir, Dr. Gopinath Sir. But for the benefit of the younger generation, like there are, I could see there are some more number of scholars are participating in this particular webinar. So for the benefit of this younger generation, just I would like to say a few words. I'll not take not more than 3 minutes time because no need of introduction about the big scientists. Okay, so when the committee has approached me to share this session, I simply accepted. Reason is there are three reasons for that. The first one is he's a very good researcher. Okay, I could see like when they said, I got something like a more than 2-3 pages of even I asked them to give a short write. Okay, they gave me some 2 pages. I said again shorten. No, it is going to be like a 1.5 page. So excellent research achievements and has a more than 250 papers, more citations and patents, especially the recent one like carbon dioxide. The patent is real. I got the patent. It has a more value to the society one. So scientists, as we do only organic chemistry, synthesis is compound, and not exposed much to the society, but people like Professor Gopinath sir is contributing valuable things to this direct to the society. So in that way, I'm very happy to introduce him. And second aspect, first one is a very good researcher. And those days, remember, we never call us a national chemical laboratory. We used to call national catalytic laboratory because the catalysis one has been contributed at NCL. I remember when I was in IIT Bombay, I used to travel to NCL and I used to interact with all the faculty members of them. So in that way, like because of the eminent people like Professor Gopinathan sir, the NCL has developed a lot. Okay, so the second one is very very important. Okay, and he's also professor in the SAR. Like they have the NCL, I mean the CSAR laboratory as a teaching component also. So he is acting as both a scientist and also very good teacher. So I came to know from my colleague who is working over there that he's also a very good teacher. Like the feedback from the students says that very good teacher. So it is very difficult to have both, as acting as a scientist and also as a teacher. But Professor Gopinath sir is having that particular one. Third one is apart from these two, that third was very, very, very important. So apart from the research and teaching, one need to be a very good human being. That okay. So because I came to know from my junior, Dr. Venkatraman, who is now in ISER, so about the research and teaching, right? Third one is only it's not meet at all. Dr. Rajkumar, don't meet all the people, please. Okay, yeah. Okay.
No, sir,
So
no,
and
sir.
that is very very important. Okay, so he's a very good human being. So whether we are good researcher, teacher, we should be a good human society. I want to share with you one small information. Whenever I attend my kids PTA, teachers meeting, okay, I used to tell them, okay, when the schools used to say, sir, you can put your son and daughter into the medical or engineering, I mean, any kind of thing. I used to tell them, I want my kids to be a good citizen. So here is the best example of that, good citizen of India. And Professor Gopinath sir, yes, sir. Then extensively, I'm collaborating with the Professor P. Selvam. So I came to know from sir, your group is also doing excellently very good work. So with this small introduction about, I can keep on talking, okay, but let us hear from sir about, uh, catalytic, and also the very, very important one, that is the conversion of a solar to the chemical energy. It's very much needed at present. Okay. So Syed is going to talk about the topic on solar to the chemical energy. Okay, and this is about chemical energy conversion. Uh, there is about clues from the nature. So let us hear about this solar energy conversion to this. So, now I sincerely thank and the organizing committee for this particular. Thank you very much.
Yes, sir. Yes.
Yeah.
Thank you,
Can I
sir.
start now?
Sir, please share your screen, sir. Gopinath,
Yeah.
sir.
First, actually, let me thank Professor Mohandas for so nice word actually about me and NCL. I'm not sure I am really what for those nice words actually, but of course NCL is popular, so I'm really happy to know that it is also called National Catalysis Laboratory. So that's first thing actually. So I'm really pleased to know that actually. And so I will let me start my talk, but I request all the participants, please mute their mic actually, because there is a lot of the vehicles passing sound is coming actually. All everybody actually. So please mute your mic actually. Okay. Except the speaker, all the others may please mute their mic actually. So let me share my screen. So uh,
Yes, sir. Please share your screen, sir.
yeah. So today I'm going to talk about the photocatalysis of water splitting actually using solar energy. So I mean here actually we try to exploit the solar energy what is really available on the in our country, entire country actually, and then how can we make use of this photon energy to chemical conversion. I am going to restrict my talk only to water splitting actually. So that's the first thing I want to tell actually. And about for the last 10, 12 years, actually, we have been doing, and I request again all of you to please mute their mic, actually, please, yeah. So millions of years, actually, our natural plants has been doing this photosynthesis very beautifully, and this has been going on for millions of years, actually, without any trouble, actually. But the only issue with natural photosynthesis, it works at a very low efficiency of 1%. 1% efficiency. What does that mean? If 100 photons are absorbed by the plant, only one electron and a hole is used for actual water splitting. So that is the efficiency. That's the way we define the efficiency. So it works. I mean, natural photosynthesis works at only 1% actually. But then, if we, I mean, but commercially, if we have to exploit actually, at least we need to increase that efficiency to 10% or even better than that actually. So that is going to be the key for this actually. So when plants are doing this photosynthesis so nicely for millions of years, actually, we are struggling too much, actually. In fact, the first photocatalysis paper for water splitting, actually, or photoelectrochemical water splitting paper appeared in 1972. And that was published by two Japanese scientists called Honda and Fujishima in 1972. It got published in Nature, actually. In fact, this is one of the highly cited paper, actually. But then they have given the proof of concept in those paper actually. But then though in fact this is 2022 actually, so we are almost 50 years down the line, and we are nowhere near commercialization. Okay, so that itself underscores that this is not a easy problem to solve actually. But then it has become a necessity because of the climate change. Recently there is a lot of change in climate actually, and that is creating havoc. So I will show you some of the picture which you might be familiar. So before going into the details, actually, I want to flash five very important question that is actually plaguing photocatalysis of water splitting. What are those actually? In photocatalysis, actually, both photophysical and photochemical processes are involved. Photophysical process like light absorption, all those things actually it requires very small time scale. Actually, I mean it works nanoscale, nanosecond, picosecond, femtosecond. It works at that time scale. Whereas all the photochemical process happens at microsecond, millisecond, and second actually. So that means it is happening at very, very high time scale. I mean the time scales are different actually, but both has to happen in photocatalysis. Light absorption also has to happen. Electron and holes has to be utilized for the water splitting to produce hydrogen and oxygen. Okay, so that means photophysical and photochemical has to happen simultaneously within that time scale of the those electrons and the charge, generally charge carriers actually. So this in the literature actually not many people have addressed actually. This is one of the important problem, but not addressed sufficiently. That's my honest opinion. And then actually see all these electrons and the holes have a lifetime of nanosecond to femtosecond, so which I already indicated actually. And then we are also working with powder catalysts. It is like actually trying to conduct electricity in broken wires. See, to conduct electricity actually, of course, over a length, actually, it is going to go down actually. But then if you are trying to do the photocatalysis in, powder material, actually, are we really going to succeed? Because to, pass the electrons or charges, actually, there should be good quality junctions actually, so that, electrons don't get, electrons don't undergo recombination actually. Okay, if it undergoes recombination, it simply fluoresces and it is just wasted actually. So there should be a good quality heterojunction. I will come to this. What is this heterojunction a little later actually, but heterojunction is really required to conduct the electricity, or can basically conduct the charge carriers for long distance actually. So that is one thing. So if we continue to use the powder material, we are not going to be successful. So what is the way out? So that's the second question. Third thing, actually, how do we bring the above aspects in powder photocatalysis, actually? Because, whether you like it or not, more than 99% of the photocatalysis papers, water splitting paper, they're all published with powder photocatalysis, actually. Should we continue to do this experiment in the same old way, or do we need newer approaches? I'm coming to that, actually. In fact, for all these three questions, actually, I got a lot of clues from the nature, actually. Only thing, there is a lot of ideas available with the nature. Only thing, we have to keep our eyes open and then, grasp those ideas, actually. So that is something, we are kind of missing, actually. Though, and another thing is actually, there are many photocatalysts are available in the literature, actually, with very, very high light absorption capacity also. But then when it comes to activity measurements, it's really, really small. So why is it so? Are we missing something? So that's something we need to think about. And then, although photocatalysis has to happen ultimately in direct sunlight, like silicon photovoltaics, actually silicon photovoltaics is actually, installed in rooftops, open ground, so that, sunlight falls exactly on that and then produce power actually. But then we don't do the experiment in sunlight, direct sunlight actually. Very, very few research group does the photocatalysis in sunlight. Why? Do we know the benefits or difficulties of doing the experiments in sunlight? Not many papers actually. If you see 1,000 papers in 1 year, actually, hardly 1 or 2% does the experiment in sunlight actually. So, but there are very good benefits actually. So, which also I'm going to highlight in my talk actually. So let me briefly tell, there are many students actually. So, the last slide was more for the advanced researchers actually, and especially for those who are doing in the field of photocatalysis. But I will go slow actually because there are a lot of students. Light is a tremendous source of energy actually. I will give some numbers actually, so which will make you understand that, how much amount of energy we are receiving on the surface of the earth actually. I'm sure many students must have read this concentrating the solar light with a lens and then creating a small fire with a paper or some splinters actually. So these are all well known actually, but then how do we make use of this energy, sunlight energy, to convert from X to Y? So that is something going to be very, very useful. And in all the major cities, actually, these type of pictures are going to be, easily. I'm sure most of you must have seen actually. So that clearly indicates that, now the silicon solar panels are increasingly being used to, to harvest solar energy into electrical energy actually. So, but the one what I show on the right side is actually, this is only solar thermal heater actually. There is no electron excitation, but only, because of the thermal effect actually, because inside this pipes actually or panels actually there is a black material is coated which absorbs light energy, and then it heats the water actually, so you get the hot water in your home actually. So that's a very simple principle. But then to harvest the solar energy into electrical energy, solar panels actually has to be installed. And then this solar panel actually, I mean, it converts solar energy into direct current actually. That's what we call DC actually. Then an inverter is there actually. That inverter converts DC into AC. Once it is converted, it can be used for the all the appliances at home, like fan, TV, computer, light, whatever actually. Okay, so this is the simple principle of converting solar energy into electrical energy. Okay, so this slide is to show that what is the amount of surface received, I mean the solar energy. So I mean surface of the earth receives about 10 to 24 joules in 1 year actually. Okay, and what we need only 0.1 percentage of solar energy, if we can harvest and convert into useful energy, that is actually sufficient. Consumption by human beings, 3 into 10 power 20 actually. So it is, though it is written 0.1 percentage actually, but I mean, if we can convert that much, it is more than enough actually. And photosynthesis on the earth requires about 10 power 21 joules actually. Just a minute, yeah. Yeah. So 10 power 21 joules actually. So all the fossil fuels actually, that means all the coal, oil, all those put together actually. I mean, what is going to be available in the next 50 years actually? If we put together, it's equal to only 10 days of energy actually. So the bottom line is actually, again, actually, I want to insist that the climate has changed drastically and it is continuously changing. We need to arrest that actually. So the best way is to, I mean, use the renewable energy like sunlight, wind energy, all those, renewable energies. If we can make use of it, actually, we will stop, adding carbon dioxide to the atmosphere. And at the same time, how to convert this carbon dioxide in the atmosphere to anything useful actually. So that also should go on actually. But our target first should be actually, can we convert the solar energy into useful energy? Even if we can convert 0.1 percentage of solar energy, that is going to be a big change actually. And if we can make use of that energy to split water and produce hydrogen from water splitting, it's going to be wonderful actually. In fact, that is going to change the presently carbon-based economy to hydrogen-based economy actually. Hydrogen-based economy is going to be very, very important, and it is already taking shape in many countries. And in India also actually, our Prime Minister has announced this National Green Hydrogen Mission on last Independence Day, and there are many, many efforts are underway actually. So with that, let me move on. And yeah, so this is just to show that, with a simple prism, actually, one can, split the white light into all the 7 colors actually, which are actually, and the corresponding wavelengths are given, which I don't want to go into the detail. This is more of a school book matter actually, so I'm sure most of you are familiar actually. So let me tell you again a little bit about the photosynthesis actually. I mean, whenever I see a tree, green leaf and plants, actually, I really, really wonder actually, because they expect nothing from us. Okay, they expect nothing from us actually, but still it gives all the thing what we need actually. Unfortunately, we human beings are not like that actually. Okay, but then let me not go into the philosophical way actually. Let me show you this photosynthesis mechanism actually, what is shown here actually. So there are two components called photosystem 2 and photosystem 1. So photosystem 2 absorbs light at 680 nanometer, and then photosystem 1 absorbs light at 700 nanometer. But what is the beauty is actually, photosystem 2 does the water splitting. The moment it is splits water, the oxygen is liberated into the atmosphere. So there is no question of oxygen combining with hydrogen. So that doesn't happen in the natural system. That's one thing. And then always there is an electron transfer from photosystem 2 to photosystem 1. Always, always. So these are the two flows. And then the proton, what is generated, proton and electron, what is generated, it is stored as NADPH. Okay, so it is stored, and then when CO2 reduction happens, because CO2 reduction is a dark reaction. So when that reaction happens, actually this hydrogen is used for the reduction of carbon dioxide to all these carbohydrate molecules actually. So there are many ideas here actually. So can we arrange semiconductor, something like this actually, so that electron flows in only one direction? That's the first thing. And then how can we achieve the thermodynamic, because water splitting is a highly delta G is equal to highly positive actually. Okay, so it's very difficult to do the reaction at room temperature. So how can we break the thermodynamic barrier actually? So that's one question which nature has achieved very brilliantly. Okay, so that's second thing. And then when proton is available, actually, how can we use that proton to the maximum possible? Okay, so these are some of the questions actually. We got some clues actually. I will elaborate those clues in the next few slides. Actually. I mean, after few slides. In fact, lately, actually, for the last 3-4 years, actually, there is one teenager girl. She's from Sweden, actually. So, I mean, she started all alone by herself, kind of war, I would say, actually, against all the governments. I mean, of course, she started with Swedish in front of Swedish Parliament, actually, and she sat in front of the Swedish Parliament and said that you bloody politicians don't take care of climate change. You better do something. You only talk, but you don't do anything actually. So that kind of movement, what she has started actually, now it has spread all over the globe actually, and she is well recognized. In fact, I think in 2019 or so, actually, her photo appeared on the front cover of Time magazine actually, so which is one of the prestigious magazine actually. In fact, most of the time actually very big, I mean very powerful people occupies that page actually. So like our Prime Minister Narendra Modi actually, and then uh, I mean Trump, so people like very high who occupy the high office actually, they occupy those space actually. But then actually, I mean, why she started this war is actually the climate change. What the climate change is doing actually, see, for example, this is a city of Venice actually, where the sea has entered into the city actually. So in the whole city was flooded actually. Okay, and you can see that the damage what happened actually. It is not only in Venice actually. Okay, so in many places actually. This is in the Australia actually. So in Australia actually, I think almost now it has become a regular affair that there are wildfires happening all over Australia actually. I mean, good amount of Australia actually. It is burning actually, especially during the summer season actually. So I mean that also adds a lot of CO2 actually. So these are some of the things. I'm sure those who are in Tamil Nadu actually. I don't have to tell actually. This is near the Chedapet actually, and where in 2015 actually the whole city was flooded actually. That was again attributed to the CO. I mean increase in CO2 concentration in the climate actually. In fact, two cities in India were identified. One is Madras and one is Pune actually. There is a lot of local heating happens just on in the city actually, that changes the climate very drastically actually. So this is one of the reason why I mean there was a too much rain and the whole city got flooded actually. So that is again attributed to the climate change. Okay, not only in Chennai actually, but it's in Kerala somewhere actually. So the whole village, I mean several villages were flooded actually. So everything was attributed to the climate change. And this is somewhere in Kolhapur actually in Maharashtra. So don't think that Chhatrapati Shivaji Maharaj is sitting on a horse and making the measurement actually. But then actually this Chhatrapati Shivaji statue is on a pedestal of about 6 feet. So that's pedestal you are not able to see actually. So you can see that damage that this flood might have caused actually. And even that poster, the supporting stand you cannot see actually. So you can see that so much amount of defects, I mean see damages happened actually. And then see, this is a very common scene. You could have seen in Chennai, you could have seen in Bangalore, Bombay, Calcutta, Delhi. I mean, all the metro cities are very vulnerable. See, I mean, all the automobiles are, releasing, carbon dioxide into the atmosphere. Actually, think about, you are one of this person who is, traveling. Actually, you are going to be exposed to carbon dioxide concentration of easily 1,000 ppm. Not, though the average concentration at the global level is 420, 425 ppm, but on the road it is going to be very, very high actually. Okay, so are we really bothered, and what are we going to do actually? So these are some of the questions actually which drives our uh, research actually. And so this is just to show that our energy dependence, that is all our energy that comes from coal, that come from oil, that come from gas, I mean the cooking gas actually, the natural gas actually. So all are, I mean, a large, almost about 85% of our energy is coming from other countries. Please remember, see, like the Ukrainian crisis, actually, if it spirals further, actually, our import dependency is going to be suffer, actually. So, yeah, similarly, if there is a problem in Middle East, again, we are going to suffer, actually. So, though the problems are happening somewhere, actually, we will be affected, actually. So, that's one thing. So, these are the factors, actually, geopolitical factors, actually, it affects India very seriously, not only India, many other countries where we don't have our own energy sources actually. So this clearly compels us that we need to go for our own energy, which is likely to be water splitting to produce hydrogen, or you convert solar energy into something useful energy. Actually, it may be chemical energy, it may be electrical energy, but if we produce, then we are safe. Okay, so this is going to be the key actually. So in fact, those who are doing research, actually, you may consider, thinking of doing research in this energy area, actually, because this is going to be very important, and it's going to be continued to be important for several decades, actually. And then when we use all these carbon-based fuels, actually, how much amount of carbon dioxide we are, releasing into the atmosphere? So this is the prediction actually, which was predicted about 2-3 years back actually. On the left side, what I show is actually 2021 prediction actually. I mean, it was predicted some 3-4 years back actually. The first one is actually, it is called BAU, that is a business as usual. We do nothing. If we do nothing and if we release all the carbon dioxide into the atmosphere, we end up about 3,300 million tons of carbon dioxide is added only in India. Okay, so this, what is CCS? CCS is carbon capture and storage. That means capture the carbon dioxide, what is coming out from power factories, cement factories, steel factories, which is the major emitters of carbon dioxide. If we can capture and store it somewhere, actually, if we can reduce the 30% net reduction of carbon dioxide, actually, will bring down the effect somewhat to a lower level, actually. The same thing for 2031 is given on the right side, actually. I mean, if we do nothing, that is the business as usual case, actually, you can see that the carbon dioxide concentration is going to more than double compared to 2021. 7,300 million tons of carbon dioxide will be released into the atmosphere, actually. So you can imagine, actually, how serious it is. I mean, even with 3,300 million tons of carbon dioxide, if we are already affected because all these climate changes are affecting us so much, more than double, it's going to be, I mean, the natural disasters are going to be much, much more, actually. Okay. So we need to clearly take care of this issue as quickly as possible. Otherwise, all, I mean, our present also will be affected, future will be much more affected, actually. Okay. This is just to, let me come back to the photocatalysis. Actually, this is the first observation what was made by Honda and Fujishima. I mean, they took a simple electrode of, made with the made with the rutile, actually, which absorbs light of UV light of less than 410 or 450 nanometer, actually. Upon light absorption, electron is excited from valence to conduction band, and with a small applied potential, actually, the electron can flow to the platinum counter electrode where the water splitting happens, and it gives small amount of hydrogen. So this was the proof of concept published way back in 1972. Okay, what we need is actually we need to have a photocatalyst that absorbs sunlight without any potential, that is unassisted. It has to work to split water and give a lot of hydrogen, actually. So this is the requirement, actually. Okay, So 50 years have passed and we are nowhere near, even the breakthrough catalyst. So that means, we need to work really hard actually. Okay, so that's first thing I want to underscore. But this also underscores that this is an extraordinarily challenging reaction and a breakthrough is likely to be considered for Nobel Prize because, it's going to change the economy from carbon-based economy to hydrogen-based economy for the entire globe. Okay, so this one single reason is sufficient to, consider for Nobel Prize. That's my honest opinion. And what are the advantages of hydrogen? Hydrogen, compared to any common fuel like petrol, diesel, actually, hydrogen is three times more than, it gives three times more energy actually. So, I mean, in 1 kilogram of diesel, whatever gives actually, or petrol, whatever gives about 44 megajoule per kilogram, it gives actually. But in terms of 1 kilogram of hydrogen gives about 120 megajoule actually. Not only that, when you burn hydrogen, you get energy and then it leaves only water as a side product. Absolutely no carbon dioxide is added actually. So that makes this hydrogen as a green fuel actually. Okay. And then hydrogen is also safer actually. In fact, many people still consider that hydrogen is a bomb actually. Though we are happy to put a gas cylinder on the backside of the car and drive whatever distance actually. But the same thing doesn't happen with hydrogen actually. So to get rid of that fear actually, is the city of Paris actually what they did actually, they employed the hydrogen cylinder fitted fuel cell cars actually in the most populated area just to get rid of the fear that hydrogen is good, hydrogen is not a bomb. As long as you use it in a sensible way and responsible way, there is nothing to worry actually. Okay, but then hydrogen definitely have very good properties, then no doubt. But then it has to come from renewable resources, so like sunlight or wind energy, whatever actually. Currently, hydrogen is produced by a process called steam reforming of methane or steam reforming of naphtha or any carbon-containing, molecules actually. So what happens is actually when we produce 1 kilogram of hydrogen through the steam reforming route, about 7 to 8 kilogram of carbon dioxide is added to the atmosphere. Can you imagine that to produce 1 kilogram of hydrogen, you are releasing 7 to 8 kilogram of carbon dioxide, which is really not acceptable. Okay, so this is what already it has caused a lot of problem actually. So, the industrialization, what happened in the last century has clearly damaged the atmosphere actually. The climate, environment, everything has damaged. So this is high time that we need to address those issues actually. In fact, I indicated earlier actually that water splitting is an uphill reaction, and to split water, the one OH bond, even to split one OH bond, we need about 495 kilojoule to split both the OH bonds actually, and to make it from water to oxygen and two hydrogen atoms actually in the gas phase, it requires about 925 kilojoule per mole actually. So you can imagine that, if we have to achieve that thermally, water has to be heated up to 1600 degrees centigrade. So even to heat 1600 degrees centigrade, you are going to spend a lot of energy actually. So which is not going to be, used. It's not going to be net energy positive. Rather it is going to be net energy negative actually. So there is no point in doing. But then plants are doing this photosynthesis beautifully actually. Okay, so even though the thermodynamics did not change, but the plants did very, very nicely. How they did actually, when the water is split, actually, oxygen immediately liberated to the atmosphere, and then hydrogen is stored. Okay, as I said in the photosynthesis diagram, actually, so since oxygen is liberated into the atmosphere, there is no question of hydrogen oxygen combined. Further, hydrogen is stored as in a DPH and used when needed actually. So that nature has overcome the problem actually. Whereas we human beings want to split the water and get the hydrogen and oxygen, but with very less effort. So this is the problem. Okay. Nature works at very low efficiency, as I said earlier, actually. So there is a lesson to learn. Actually, we are too greedy to be frank to say that actually. So let me just share a couple of slides on what is the fundamental process in solar harvesting, especially for water splitting. There are hundreds and hundreds of semiconductors are available which can absorb sunlight or part of sunlight. Okay. Upon light absorption, an electron is excited from valence band to conduction band. So that's the first step. So that means electron and the hole, a pair is created actually. That's the first step. It happens with in I mean almost all the I mean many semiconductors. In the second step, what should happen is actually the electron hole pair created should be separated, and the electron should move to the reduction co-catalyst, and hole should go to the oxidation co-catalyst. It should not undergo recombination. If it undergoes recombination, that's the end of it. It will simply fluoresce and nothing will come out actually. So the second step is going to be very, very critical. Once the second step is successful, there are co-catalysts available on the surface of the semiconductor, I mean, which is absorbing light, and then water splitting can happen at respective co-catalyst actually. So that's the third step. So third step is the utilization of the charge carriers. Okay, step is the very, very critical step. Okay, so that is a place where many things are going to be. Many special requirements are there. This is the sunlight spectrum, what I'm showing on the left side. Actually, the visible light percentage is actually 45% of the sunlight contains visible light, somewhere from 400 to 800 nanometer. Below 400 nanometer is UV, which is about 5%, and above 800 nanometer, it is near IR and IR actually. So the remaining, I mean, near and IR itself will contribute about 50%, which is effectively not going to be useful actually. What is the basic requirement? Some more basic requirement for water splitting. So for water splitting to happen, actually, conduction band of that photocatalyst should be, lower than the water reduction potential of 0 volt actually in the normal hydrogen electrode scale. Similarly, for the water oxidation to happen, it should be higher than the water oxidation potential of 1.23, including some more potential. It can be, it should be at least 1.6, 1.7 volt actually. So, I mean, this is the basic requirement actually. So, I mean, if some material is not meeting this requirement, then forget about, nothing will happen actually. Okay. Though there are hundreds of semiconductors are meeting that requirement, but still, we are far away from the achieving a good efficiency. What are the reasons? Photocatalysts actually should absorb actually. I mean, when we talk about visible light, I mean sunlight, we have a few percentage of UV, but a percentage of visible light. Again, visible light, there is a long range of wavelength ranges there actually. So can we absorb the maximum amount of visible light and UV light? If we have to do that, actually, one material cannot absorb in the entire range. So that means we need more than one material, maybe two, maybe three, maybe four actually. So in that case, actually, we need to combine them. We need to combine them in a composite actually. So in that case, actually, composite can absorb light, but then electron and holes has to be separated, and it has to travel to a long distance to meet that redox co-catalyst actually. Then only the reaction will happen. If the electron and holes recombine, again there is no use. So when we combine more than one material, the heterogeneity comes actually. So they need to be, they need to bond very nicely through good quality junctions. So this is called junction. And since the materials are, it may be different types actually. It may be P-type semiconductor, N-type semiconductor, or maybe metal actually. So that's what we call heterojunctions actually. Okay. So the nature of materials are different. So the number of heterojunctions and the quality of the heterojunction decides how efficiently they can separate the electron and hole pairs. Okay. So charge recombination. I mean, after generating charge, if they recombine again, there is no use. So how to minimize the charge recombination? That's another big issue. Of course, this is another routine issue actually, which is more of how to optimize the surface area on crystallinity, which is not a difficult problem, which we can achieve very easily. There are many synthetic procedures are there. But the major problem is actually, even if we have 3-4 material which can absorb light with good surface area and crystallinity, and how we are going to integrate all those materials, and how we are going to integrate electronically as well as structurally. That's going to be the key actually. If it is simply a physical mixture, it is not going to work. It has to be integrated actually. So the integration brings the better and better activity. Ultimately, the material has to be stable in the medium where we are going to do the reaction. So basically, that means it has to be stable to the light as well as in the water, because we are going to do the water splitting. So that means it has to be stable in water. So the idea is optimize all the parameters in one material and make it as a workable catalyst. So that is the challenge. So you have to meet some 10 different needs in one material. So that is the critical challenge actually. And let me come to the point what from where I started actually. So this picture clearly shows that the blue arrows are the the favorable arrows, the red arrows are the unfavorable arrows actually. For example, the light absorption again given in blue, the electron excitation from valence band to conduction band that's given in blue. So they're all good. They're all good. But then the recombination is given in red. Okay, so recombination is not good because if electron and holes undergo recombination, it is of no use. Okay, all the chemical reaction, what is photochemical reaction, what is happening, the reduction, oxidation, what is happening, they're all good actually. But then the major issue here is actually the time scale difference, what I mentioned earlier actually. So all the photophysical process works in very, very small time scale, whereas photochemical process works at very high time scale. So that means further actually the electrons and I mean generally the charge carriers live very, very short lifetime actually of the order of nanosecond and less actually. So how effectively we can diffuse the electron and disperse the electrons in an ensemble of particle actually. Loss of electrons decide the success and the efficiency actually. So this is the place where good junctions are going to play a major role. Otherwise, when we do the reaction in powder material, it is like trying to conduct electricity through broken particles actually, broken wires actually. Okay, so that is the thing I want to underscore actually. Let me simplify one more issue actually. Okay, so here actually I'm displaying a table and two blue squares and two red squares are there actually. This is again for the water splitting and which was reported in Journal of American Chemical Society in 2010 by a well-known photocatalysis scientist called Kazunori Doman actually, who is a top person in photocatalysis. In fact, he has dedicated his life for photocatalysis. But the message here, what I want to give is actually when the photocatalyst amount is 75 milligram, they are getting a efficiency of 6.3% apparent quantum yield or simply efficiency. When they increase the amount of catalyst from 75 to 150 milligram, you can see that the efficiency has come down more than 50%. Can you imagine that increasing 75 milligram to 150 milligram of powder material, bringing down the efficiency more than 50%? How can we scale up to 1 gram and then 10 gram, 100 gram or kilogram actually? This is clearly not going to work out. So the powder material, I mean, evaluating powder material for photocatalysis itself is not correct actually. That's my honest opinion. So we need alternate methods actually. This is the place where we start looking at the nature. I mean, if you look at the nature actually, I mean, you look at the leaves actually. All the leaves are, you can compare it as a thin film actually because it is a single piece. Okay, whereas powder we cannot compare to a thin film actually. So can we make our powder catalyst as a thin film? I mean, just simply deposit on a substrate and evaluate. So that was the simple idea we generated. Okay, so then we did that, and I mean, the activity jumped at least 10 times. Okay, so then we realized that connecting particles is very, very important. So I'm going to show two videos actually where a small amount of 0.28% of palladium deposited on titania, simple titania. Titania absorbs only UV light, please remember. And then it is coated as a thin film and then evaluated for water splitting with aqueous methanol. It's the same reaction we carried out at 10 o'clock as well as at 12 o'clock. You can see that the shadow. The amount of bubbles involved from around 12 o'clock is could be that video that is part of the time. 12 o'clock, the temperature has increased. The temperature is the solution temperature has increased. So what happens to the rate of the reaction, rate of water has required. So not only that, actually, when we did the same reaction in laboratory condition, actually, we hardly see a small amount of hydrogen actually. I mean, we could not see any bubbles like this actually. So that clearly indicates that sunlight definitely have role actually. Okay, so it is best to do the reaction in sunlight. So that's the first message I want to give. And then we explored the nature of the, I mean, structure of the leaf, microstructure of the leaf a little bit more actually. In fact, there is a good paper available in advanced material that also was published in 2010. One thing I want to underscore here is actually there is a red square I have given actually. So on the top surface, when the sunlight passes through the top surface of the layer and then goes through the one-dimensional palisade layer, actually one-dimensional pipe actually, once it enters through the leaf, it will never able to scatter back to the atmosphere. It will be internally scattered and eventually fully absorbed actually. Even though small amount of light penetrates into the leaf, the entire percentage of light is absorbed. So that is, so this natural micro nano architecture actually help for the light absorption in a very, very efficient way. Combined with the photosynthesis scheme, actually, we arrived at many factors actually. In fact, I will come back to this later actually. See here actually, as in photosystem 1 and photosystem 2, they are energy arranged so that electron flows in only one direction. So can we arrange semiconductors and mimic the nature? So that's the first thing. Second thing, can we have different, I mean, by arranging different semiconductors which have different band gap actually, so we will able to absorb light of different wavelength actually. So that way we can maximize the absorption of different wavelength region of sunlight. Can we absorb UV visible as well as near IR? So can we combine 2-3 semiconductors in such a way that it absorbs the entire range? So that's one thing. And then third thing is actually photosystem 1 and photosystem 2, and all the natural components are connected directly. There is no wire in between. So how nature has assembled, and nature has assembled, it is not mixed actually. That means molecules and ions and atoms are coming one by one and getting assembled in the natural system of leaf actually. So how can we achieve that? So this is the place where I am going to show this particular synthetic procedure, which is called Cellar method actually. Uh, select ionic layer and absorption and reaction method actually. So here actually Cellar method actually where for example, we make a titanium film, which is a porous titanium film actually, and then first dip it in cadmium solution. A single layer of cadmium is absorbed all over the surface, okay, especially in the pores. Then followed by sulfide. Okay, this cycle is repeated. So wherever cadmium is there, sulfur also gets bonded actually. So a cadmium sulfide, a molecule forms. In the subsequent cycle, actually, the size of the particle grows actually. So you have the control to grow the particle to the required level actually. So here actually we are assembling the ions in the pores by this successive ionic layer absorption and reaction method actually. So cadmium sulfide and lead sulfide was assembled in porous titanium. So that was the method we used actually. So this also leads to the wireless heterojunctions actually, because cadmium sulfide directly deposits on titanium layer and forms a very high quality heterojunctions. You don't need any wire actually. Okay. The another thing is actually, since it is, deposited as quantum dots, actually the light absorption becomes no problem actually. So this is another clue what we got from the nature actually. As in the natural photosynthesis, oxygen escapes to the atmosphere. Here, actually, what to overcome the thermodynamic barrier, we use the sacrificial agent actually. So that way, actually, we are able to simulate the nature from the clues what we got actually. So we made 3 photoanodes actually. One is a pure titanium, which is given as 1, and second is the same titanium layers. Lead sulfide and cadmium sulfide is assembled into the pores. In the third one, actually, which is slightly greenish yellow, that is integrated with a small amount of gold. Actually, you can see that the gold, titania, lead sulfide, cadmium sulfide, which is given as 3, which is in the UV visible absorption is given in red color. You can see that it absorbs UV light, it absorbs visible light, and then absorbs a limited amount of near IR light also actually. So, and when we look at the chemical distribution of all the elements, we could clearly see that the thin film of about 8 micron, the lead sulfide, cadmium sulfide is uniformly distributed right from top to bottom. So that means quantum dots are available in the pores for the entire 8 micron thickness actually. So that's first thing. So like that, we made several photo anodes, and we measured the activity, and we could see maximum activity with the gold titanium sulfide and cadmium sulfide, which we also evaluated for the several cycles, and the activity seems to be stable. With 1 square centimeter film, which contains about 2 milligram of the material, photoanode material, it gives about 500 micromoles of hydrogen per hour in presence of light, in presence of sunlight or one sun condition actually. This is with 2 milligram of material I'm talking of 500 micromole actually. So you can imagine. So let me not go more actually, because I'm sir, can I take another 5 minutes?
Yes, sir.
Sir.
Please proceed, sir.
Yes, sir. Yes, sir. Please, sir. Please go ahead. Sir.
Okay, so this is just to explain the mechanism of the photocatalysis, what we reported actually. So here you can see that the arrangement of the, I mean, the band arrangement of cadmium sulfide, lead sulfide, and titanium, and then gold acts as a surface plasma resonance of gold actually through field effect it happens actually, and the electron transfer also happens from cadmium sulfide to lead sulfide to titanium. So that means electron flow will be in only one direction. So that way we are able to simulate the nature actually. So here actually, I mean, arranging the quantum dots and arranging the quantum dots in the right order is the key actually. So this is what I want to highlight with this particular slide. Another small example is actually, see nowadays we are using LED lights everywhere actually. So LED lights are meant for giving light emission actually. So light emission happen because of the recombination actually. So inevitably recombination happens in any system actually. So can we make use of this recombination as a source of light for further absorption, further light absorption? That was the a crazy idea we had actually. So what we did is actually I mean, the literature, and we realized that manganese doped cadmium sulfide is a white light emitting semiconductor actually. So we used that particular actually. So what we did is actually assembled only cadmium sulfide in titanium. That's the light absorption, EV visible absorption in gold. And then manganese doped cadmium sulfide is assembled in titanium. You can see that.
ஹேண்ட்புக் அடிக்கக்குள்ள நம்மளோட டைம் டேபிள் மட்டும் தானே போட்டுக்குவோம். ஆமா இன்சார்ஜ் நம்ம கிளாஸ் டைம் டேபிள்
Rajkumar.
Yes, sir. Yes, sir. I am checking and I am mute of the discussion.
Unmute, please.
Yes, sir. Yes, sir. Sir, please proceed, sir.
Gopi, sir. So you muted.
Sir, your voice is.
Yeah, now it's okay.
Yeah, yeah.
Yes, sir. Yes.
Okay. So now I'm sorry actually. Maybe you might not have heard actually. So here actually what I want to say is actually the manganese doped cadmium sulfide emits light from 400 nanometer, which can be absorbed by the manganese doped cadmium sulfide itself actually, because we are able to integrate the manganese doped cadmium sulfide of different particle size. It is 2 nanometer, 3 nanometer, 5 nanometer. So what happens is the light emitted by 2 nanometer can be absorbed by the higher particle size. So basically we are able to absorb the light what is emitted by a smaller particle but by a bigger particle actually. So basically we are able to improve the light absorption and amount of charge carrier generation, that improve the efficiency to about 7%. Actually, the previous system was about only 5.5%. So maybe I will skip this particular slide because it's not very maybe not so relevant right now. Actually, sorry, I'm going to conclude my talk. Actually, here actually see I'm. Recently, we wrote a review actually in Journal of Materials Chemistry A. It is almost 1 year old, and here actually we have clearly insisted that it is not the powder form, it is the thin film form going to improve the solar hydrogen generation. And what are the ways to do that? Okay, so that's what we have highlighted in this particular review. Let me go through this this couple of lines what we have written. By adopting a number of small but significant changes, solar hydrogen production can be enhanced. The present review discusses such different approaches employed for photocatalytic water splitting reported in the literature. For example, an increase of up to 2 orders of magnitude in solar hydrogen generation was observed with a film form compared to the particulate form of the same catalyst. Discussion on various approaches of enhanced hydrogen production under sunlight and one-sun condition is the main focus of this review, in particular with thin film forms. Okay. So like this, we have discussed few things, and we also suggest that we believe the presently practiced diverse evaluation efforts may be truncated to fewer methods such as film-based evaluation and in a focused manner to tackle the solar water splitting issues towards sustainable production of solar hydrogen. Okay, so with that, let me conclude my talk, and I want to make few suggestions, especially for those who are working in this area. Consider seriously to move from particle suspension to thin film measurements. I mean, when you do the photocatalysis measurements, this is going to increase the rate of the reaction very, very efficiently because it is going to absorb the light also, and then charge utilization also happens actually. So ultimately, we'll be able to make possibly a patent and good quality publications. Okay, so and then try to mimic the nature with your catalyst and the experiments, and please keep your eyes wide open and observe the nature to the maximum extent possible. Don't just synthesize your material, but assemble them from ionic and atomic species. That is likely going to help better actually. And water splitting experiments, the overall water splitting, that means without any sacrificial agent, it is going to be really slow actually because of the 4-electron process of oxygen production. So rather to make a quick progress, actually, one may use sorry, cheaper sacrificial agents like glycerol or cellulose. So that's one of my suggestions. And then carry out the experiments in directional light. Don't do the experiment with standard light. Actually, I mean, of course, you can do that for very if whenever quantification is required. But otherwise, actually, because ultimate application has to happen in directional light, there are definite advantages which I have shown. So please do that experiment, and it is very easy also. A simple wet lab is sufficient to do all this measurement. Okay. And then I also request any of you who are investing time in dye discoloration. I'm also happy to disagree that it is not a degradation. It is only discoloration experiment. Rather move to chemical conversion of A to B. Okay, so that you can value add to your research actually. So in dye discoloration, actually, we only observe that the visible light absorption, decrease in visible light absorption, and we conclude that dye has degraded. No, it is not. You are only breaking the dye components into 2, 3, 4 components. Okay, it is not completely mineralized. That means mineralization means all the carbon should evolve as carbon dioxide. We don't wait till that time actually. Okay, so it is only discoloration, it is not degradation, and you need not waste time in this particular experiment actually. So that's my honest opinion. And or you may do a simple reaction like alcohol to aldehyde or ketone. That kind of experiment are going to add value to the research actually. Okay, so let me conclude my talk. And when we published our the thin film based paper in 2017, it was appreciated by Nature India first, followed by many media reported actually about our work. And I really want to say that sustainability is the key, and conclude my talk. And I want to thank all my wonderful students. Actually, I'm really fortunate to have brilliant students. Actually, they are all helping me, and because of them only, I'm able to talk to all of you actually. And good amount of funding also came from TAPSAN, CSCR, and NCL. With that, let me conclude my talk, and I'll be very happy to take any questions you may have. Thank you. Yeah.
Yeah. Very useful and eye opener, I would say, like for this, especially for the younger generation people. Like, sir has clearly mentioned about the climate change. Whether you save any kind of thing like money or house for your future generation, you must take care of the climate. Otherwise, the entire world is going to be in disaster. So as a chemist, our contribution is very important. Okay. So sir has clearly mentioned about CCS, that is carbon dioxide capture, okay, and storage. So even if you are not able to degrade it, at least make it into some useful material. So that is very important one. So maybe if there is any questions from the students, from the from participant side, one or two questions. Maybe 10. Dr. Rajkumar, is there anyone who has put up in the chat box? We can ask questions, because normally if you allow the student, the participant, it will take more time and unmute all. Okay, sir, I have a few questions. Because we are working on organic chemistry, and especially the synthesis of the carbohydrate derivatives. Okay. So this carbohydrates, having a carbon hydrogen kind of system. Okay. And when you react these to carbon dioxide and water, okay, it's a well-known reaction that sir, photosynthesis one. So apart from this proton, like which recombine, and the electron which recombine, is there any other things like plays an important role in this particular?
Yeah, I think it's a very good question actually. In fact, my group is already working in this area actually. Though I have very nice, but we are going. But I can tell you, briefly what is happening actually. So we are able to convert carbon dioxide into value chemical. Okay. So at least we are, both carbon dioxide activation and the water activation happens simultaneously in presence of sunlight, and then we are able to produce methanol. We are able to produce formaldehyde also, and under certain conditions, actually, we are even able to produce ethanol. So that means CC coupling also happens. But of course, slightly different conditions with different pathways, all those things actually. So here, tuning the redox potential of the valence and conduction band of the material is going to be one of the key. And then what is the right co-catalyst we can make use of it, so that you go to a desired product like ethanol or methanol. Okay. Because there is a lot of value addition we are doing here. So, but we got some clue, and I believe we have taken our first step in the right direction. I would say actually not more than that.
Yes, sir. Yes.
Okay. So,
actually, it's a lengthy process. Okay. We have to, the 6 carbon generation, glucose generation is a lengthy process where we need to produce first the methanol.
Yeah. So we are on the process actually. Hopefully, in the next 1 or 2 years, we will. We may publish an excellent paper sometime soon. Then I will able to give a talk, sometime later actually. Okay, yeah. Thank you, sir. Yeah, and
Thank you, sir. Thank you, sir.
Venkatraman has raised his hand. Venkatraman, can you?
Hello, Dr. Gopinath. This is how are you? Yeah, it's very nice, wonderful talk, and excellent presentation. So I should say a lot of notes I took it, especially the data that the history. So my question is a little goes on that curiosity based, like as you said, like we have not yet completely learned from plants, so I think that itself shows that that very intricate things, but we, as you explained very nicely, photosystem 1, photosystem 2, manganese based material. But still, do you from your point of view, like do you see that it is possible to sometime to really reach out? Because nature does any process, nature does so efficient. That is the thing. But whether we are not able to understand that and do, or is it so intricate that we, because thermodynamics, everything nature does in a very, takes care in a very nice way. So what do you think, like we can still go about it and we can still achieve at least certain percentage of what nature does?
Yeah, yeah, it's an excellent question, Venkat. Actually, thanks for asking this. Actually, see the effort what is taken even at global level. I would say that we have just touched the tip of the iceberg kind of thing. Actually, I mean, what nature has done, we have only touched the tip of the iceberg. Actually, I mean, there is large amount needs to be explored. Actually, see, for example, the natural photosynthesis involves both organic and inorganic components. Okay, but then we want to do everything by inorganic system. Okay, that itself is a big contradiction. Actually, will be able to do that? That itself is a question. But then natural photosynthesis happens actually. But then every year all the trees shed their leaves actually because of organic. Actually, if it is only inorganic, it won't happen actually. It will live forever actually. So the approaches needs to be focused towards that. If we can do inorganic system, all inorganic system, then how do we bring that quality of the heterojunction? That itself is one big question. Okay, so like that, and then how do we integrate structurally, microstructurally, electronically, because we are talking about conducting electrons over long distance actually. So through inorganic system it is possible, but then how are we going to integrate electronically, structurally? I mean, these are the questions not touched upon. When we start exploring this thing, we will start understanding the natural system better and better actually. So we will get more and more clues to solve this problem actually, which we have to do as quickly as possible. We may have to focus our research on such a problem that are pressing us actually, because see, we also have the obligation to preserve the nature for our future generation. Please, we should not forget that actually. Okay, we have destroyed to a good extent, but those guys who are the new millennials actually, for them actually, what are we leaving actually? That's a big question actually. I myself asked several times, so can I do something? So I mean, all my research is focused towards that actually. So can I clean up the environment to some extent at least through my research? If you can do that, nothing like it. So because the research satisfaction comes when your work is going to be applicable to the society actually. So
yes, sir. Yeah, that is correct. Actually, that is very good. Actually, so actually, artificial photosynthesis and producing a one drop of blood by ourselves. Okay. So these are some of the challenges. Nature does very easily, but it is very. But we can make an attempt. We can make a try, and then we can go to some level where we can able to do so. Thanks, Dr.
Thank you so much.
Yeah, how are you? Fine.
I'm fine with Mohandas. Thank you. Thanks.
Okay.
Hello,
Okay,
Gopinath. I have one doubt regarding the material. So you
Yeah.
said that the Silar technique having a combination of various metals, right? So high entropy oxide, multi-component system. So how far it will be a updated one, which is related to the carbon capture. So when we are mixing.
no, you want to make iron oxide with carbon.
So multi-component metal oxide. So when I mix it, yes.
So here actually say just a minute. Yeah. Yeah. So here actually see nature has assembled actually. Okay, it is not made and I mean mixed actually, but rather assembled actually. So to assemble mean actually you need to have a pore first of all. Okay, so that's what you take your base material as a porous material, like a porous titanium, porous zinc oxide, whatever actually. In that pore, you start assembling with ionic components. If you want say iron oxide, you have to put the ions and anion actually counter anion, so that when you calcine you may get an iron oxide of again of course you have to optimize a lot actually. Okay, so when something like cadmium sulfide, cadmium is cation and sulfide is anion. you are able to assemble very nicely. Okay, so you are able to assemble cadmium sulfide of a required quantum dot size in the pore actually. If the pore size is 3 nanometer, you cannot exceed more than that. So that pore size itself, uh, restricts the growth actually. Okay, so some such approach you may want to use to, assemble the light absorbing components. Okay, you
So
might
the
want to go through one.
perovskite,
Yeah.
perovskite material, if we are replacing that A into some other combination of metals, that should leads to give a multi-component oxide. So hence we can able to get a high entropy oxide. So by that, it will be hopeful for the carbon capturing at this trend.
Yeah, so here actually see, I mean, we also started working with a simple component actually. Okay, say like cadmium sulfide, lead sulfide. I mean, we are able to go up to that level. I mean, increasing the complexity to, perovskite, spinel, that kind of thing, it requires even more efforts actually. Okay, because, assembling two different ion, two different cations you are talking here actually. When you say perovskite or spinel or whatever actually, two different metal ions itself in a particular ratio you want to assemble, and then you want to go to that particular structure, it is going to be really difficult actually. So, but anyway, efforts should be made in that direction, but with very, very controlled way actually. So, I mean, it requires time, but it's not impossible actually.
Okay, sir. Yeah, yeah. Very nice discussion, sir. Actually, like, and I'm sure, like, out of this, I think around 100 participants are there. Definitely, this will be more useful for this, the participants to start with, to take care of our, climate change, and we should do something for the environment. Otherwise, in future, like another 20, 30 years, you will not have any source of, energy. So we as a scientist, as a chemist, okay, we must take care of it. Okay. So thank you so much, sir, for your
So
nice
thanks so
presentation.
much. I'm
Okay.
really happy
Excellent.
to be part of this.
So
Yeah.
once again thankful for your fruitful
Yeah.
time.